Imagine a huge object, 6 miles wide, speeding through space at 12 miles per second toward Earth. 66 million years ago, an asteroid like this crashed into what is now the Yucatan Peninsula, creating the Chicxulub crater and causing a mass extinction. Today, our planet is still at risk from near-Earth objects, including asteroids and comets that pass close to us. NASA and other space agencies have made great progress in tracking and understanding these dangers, but the risk is still there. With advanced technology, scientists are developing ways to monitor and reduce these threats, from using kinetic strikes to gravity tractors. But what would happen if another asteroid the size of Chicxulub was headed for Earth? How ready are we for such a disaster? About 66 million years ago, something happened on Earth so devastating that it forever changed the planet's history. A massive asteroid about 6 miles wide collided with what is now the Yucatan Peninsula in Mexico, creating the famous Chicxulub crater. The immediate consequences were nothing short of catastrophic. The collision unleashed energy equal to billions of nuclear bombs, starting massive fires, triggering giant tsunamis, and hurling huge amounts of debris into the sky. However, the most lasting effect of this impact was the thick cloud of dust, soot, and sulfur that shot into the atmosphere. These particles formed a global haze, blocking sunlight for a long time, an event scientists call impact winter. This darkness caused temperatures to plummet, disrupting ecosystems and leading to the extinction of many species, including the dinosaurs. New research published in Nature Geoscience in October 2023 has revealed the crucial role that tiny dust particles, particularly those between 0.8 and 8 micrometers in diameter, played in this global climate disaster. These fine particles were the main contributors to the abrupt and severe climate change that followed the asteroid strike. The researchers collected rock samples from North Dakota that are 66 million years old, taken from an area far from where the impact occurred. These rocks contained surprising amounts of fine dust particles, which had spread across the atmosphere. This dust formed a thick, persistent cloud that hung around for as long as 20 years, with the first 5 to 8 years being the most intense. During this time, the Earth was shrouded in darkness, causing a dramatic drop in global temperatures, with a chilling 18 degrees Fahrenheit decrease in just the first year. As sunlight was blocked out, plants were unable to perform photosynthesis, which is the process they need to produce food. Without food, plants began to die. This caused a chain reaction, starting with the plant-eating dinosaurs, which starved to death. Without these herbivores, the carnivorous dinosaurs that hunted them also perished. As a result, about 75% of all species on Earth became extinct. What's particularly interesting about this new study is that it reveals the important role dust played in this extinction event, which had been overlooked in previous research. In the past, scientists believed that soot and sulfur were the main contributors to the cooling of the Earth because they block sunlight more effectively. However, this study shows that while soot and sulfur were indeed significant, the sheer volume and lasting presence of dust had an even deeper impact. The study also explores how some species manage to survive the long, dark period. It suggests that plants and animals with the ability to hibernate or adapt to these harsh conditions had better chances of survival. However, the study raises questions about the survival of freshwater organisms, suggesting that more research is needed to fully understand how different species were affected by the impact. Near-Earth objects, NEOs, are asteroids, comets, and other space objects whose orbits bring them close to Earth. These objects vary in size, ranging from small, harmless rocks to massive bodies capable of causing catastrophic damage. Asteroids are rocky remnants from the early solar system, mainly located in the asteroid belt between Mars and Jupiter. Comets, on the other hand, originate from the distant regions of our solar system and are made up of ice, dust, and rocky material. As they get closer to the Sun, comets develop glowing comas and tails, creating a stunning display. The danger these objects pose depends on their size and path. While most NEOs are too small to cause significant harm, some, like the Chicxulub impactor, have the potential to trigger global disasters. To monitor and reduce the risks from these objects, space agencies like NASA and the European Space Agency, ESA, have developed extensive programs to track and detect NEOs. Telescopes around the world are constantly scanning the sky, identifying and cataloging objects that might come near Earth's orbit. A key tool in this effort is the Wide Field Infrared Survey Explorer, WISE, which has been repurposed for the NEOWISE mission. This space telescope has already discovered and studied hundreds of near-Earth asteroids. One of the most exciting developments in NEO detection is the use of artificial intelligence, AI. In May 2024, an AI algorithm called Trackletless Heliocentric Orbit Recovery, THOR, made an incredible breakthrough by detecting more than 27,000 previously unknown asteroids in archived telescope images. This AI system can analyze vast amounts of data and track objects with remarkable efficiency. It can process up to 1.7 billion points of light in a single image and then piece them together into asteroid trajectories. Soon, the Vera Rubin Observatory will begin operations, further enhancing our ability to detect NEOs. Equipped with advanced AI software like HelioLink 3D, the observatory is expected to catalog millions of asteroids in just the first few months, doubling the current number known to scientists. Despite these advances, no NEO is large enough to destroy the entire planet. However, asteroids that are about a mile or more wide could cause catastrophic damage on a global scale. For this reason, NASA has been focused on detecting and tracking these larger NEOs. By 2021, NASA had detected over 90% of the largest objects, ensuring none of them pose an immediate threat to Earth. While smaller NEOs might not be able to destroy the planet, they can still cause significant regional damage. Take, for instance, the asteroid Apophis, named after the Egyptian god of chaos and destruction. Discovered in 2004, this 1,000-foot-wide asteroid initially caused concern because early calculations suggested a possible collision with Earth in 2029. However, later observations ruled out this possibility, confirming that Apophis will safely pass by Earth on April 13, 2029. During this close flyby, the asteroid will come within 30,000 miles of our planet, closer than some high-altitude satellites. This provides a unique opportunity for scientists to study the asteroid in great detail. As Apophis makes its close approach, it will be visible to the naked eye from certain regions, appearing as a bright moving dot in the sky. This rare event will give scientists the chance to study its size, shape, and composition in ways never before possible. NASA's Goldstone Deep Space Communications Complex in California will play a vital role in observing Apophis, using radar to gather detailed information about the asteroid's surface features and rotation. In addition, the NEOWISE mission will provide further observations, focusing on Apophis's surface roughness and composition. These invaluable data will help scientists improve their understanding of near-Earth asteroids, allowing them to better predict potential threats in the future. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, is set to make an incredibly close approach to the asteroid Apophis during its upcoming flyby. This mission is packed with exciting goals. The spacecraft will study the asteroid up close, offering detailed observations far beyond what ground-based telescopes can provide. One of its key tasks is to collect information about Apophis's composition, surface structure, and any changes it undergoes as it passes near Earth. Using advanced instruments, OSIRIS-APEX will peer inside the asteroid, uncovering secrets about its internal makeup. This data won't just help us understand Apophis, it will shed light on how our entire solar system formed and evolved over billions of years. The close approach of Apophis in 2029 has caught the attention of scientists worldwide. Teams from various international space agencies are gearing up to observe the asteroid using a mix of ground-based telescopes and space missions. As part of the Near-Earth Object Legacy NEOLE project, researchers from Julius Maximilian University in Würzburg have proposed innovative ideas for smaller spacecraft to join the study. One concept suggests deploying a tiny satellite to accompany Apophis for 2 months, capturing high-resolution images and gathering critical measurements. Another proposal involves combining this effort with the European Space Agency's upcoming Ramesses mission, which aims to deliver even more comprehensive scientific insights. Though Apophis poses no immediate threat to Earth, its close encounter presents a once-in-a-lifetime opportunity to deepen our knowledge. By studying the asteroid up close, scientists hope to refine strategies for planetary defense, measures designed to protect Earth from potential asteroid impacts. One of the leading defense methods is the kinetic impact strategy. This involves sending a spacecraft to slam into an asteroid at high speed, altering its path to steer it away from Earth. NASA successfully tested this approach in 2022 with the Double Asteroid Redirection Test, DART. In this mission, the spacecraft targeted a smaller moonlet called Dimorphos, which orbited a larger asteroid named Didymos. The collision was a success. Dimorphos's orbit was visibly altered, proving the method's effectiveness and providing invaluable data for future missions. One intriguing idea scientists have proposed is called the gravity tractor. This method relies on the natural pull of gravity to gradually steer an asteroid away from its collision course with Earth. Here's how it works. A spacecraft is positioned near the asteroid and hovers there steadily. The spacecraft's gravity exerts a tiny but constant force on the asteroid, which over time nudges it onto a safer path. While this technique has yet to be tested in real-life space missions, it holds great promise for handling asteroid threats, especially when detected far in advance. In more extreme situations, another approach involves the use of nuclear explosions. This method would involve detonating a nuclear device at a safe distance from the asteroid. The explosion wouldn't destroy the asteroid outright, but would vaporize part of its surface. This reaction would act like a powerful push, causing the asteroid to change its course. However, this idea comes with significant controversy. Using nuclear weapons in space raises serious legal and safety concerns, not to mention the unpredictable risks involved. Still, it's considered a last resort option for deflecting a dangerous asteroid. Both approaches highlight humanity's growing determination to protect our planet from cosmic threats. To get ready for possible asteroid impacts, the International Space Agency regularly holds simulations and drills. These exercises help improve our ability to detect, track, and even deflect asteroids that could threaten Earth. Protecting our planet from such dangers is a global challenge that requires countries to work together. For example, in 2021, NASA took part in a worldwide planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. During this event, participants practiced responding to a hypothetical asteroid that was on a path to collide with Earth. This exercise allowed them to test their plans and strategies in a simulated crisis. As we continue to develop better ways to defend our planet, international cooperation and advances in technology will be crucial in keeping us safe from threats that come from space. These efforts are becoming even more important as we learn more about the many different types of space objects that could pose a danger to Earth. Working together, sharing knowledge, and building new technologies will be key to protecting the planet in the future. Asteroids and comets are often seen as very different types of objects in space. Asteroids are like old leftover building blocks of the early solar system, mostly found in the belt between Mars and Jupiter. Comets, on the other hand, are like visitors from the farthest corners of our solar system, made of ice, dust, and rocky material. But there are rare objects in space that don't fit easily into either of these categories. These objects have features of both asteroids and comets. One interesting example is an object called 2005 Q173, discovered in 2005. It behaves in ways that mix the qualities of both types of space bodies. While asteroids usually don't do much, just quietly orbiting the Sun, 2005 Q173 is different. As it gets closer to the Sun, it starts to act like a comet, releasing dust and forming a long, thin tail. This is a big clue that there's more going on with this object than just the usual behavior of an asteroid. 2005 Q173 has a 5-year orbit around the Sun. For most of its journey, it stays in the outer part of the asteroid belt, far from the Sun, but when it gets closer, it shows dramatic comet-like activity. The dust and tail it releases as it nears the Sun are a mystery that excites astronomers. In 2021, astronomers using a system in Hawaii designed to spot asteroids with potential impact risk noticed something unusual: an object with a tail, just like a comet. Further checks by other observatories confirmed this comet-like behavior. The 450,000-mile-long tail suggested that the object is likely covered in ice, which turns into gas when heated by the Sun. This process creates the tail as the gas pushes out dust and debris. What's particularly interesting about this tail is how narrow it is, showing that the dust is barely leaving the object at all. The particles are moving incredibly slowly. Normally, such slow speeds wouldn't allow the dust to escape the object's gravity. Scientists are puzzled by this, and one possible explanation is that the object's fast rotation might help fling the dust into space. In addition to unique objects like the 2005 Q173, many other near-Earth objects, NEOs, pose a potential risk to our planet. The European Space Agency keeps a detailed list of these objects, carefully tracking those with any chance of colliding with Earth. This list includes key information about each object's size, speed, and the likelihood of an impact. Right now, the list has more than 1,600 such objects. The risk is measured using a system called the Palermo scale. This scale works like a ranking system, using a logarithmic method to assess the potential danger of each object. It considers 3 factors: the size of the object, how fast it's moving, and how likely it is to hit Earth. The higher an object's score on the Palermo scale, the greater the risk it represents. Through detailed statistical analysis of these NEOs, we know that while most pose little to no threat, some are more worrying and need to be closely monitored. For instance, the size and speed of an asteroid play a huge role in determining how likely it is to impact Earth and how much damage it could cause. Asteroids that are larger than 1 kilometer in diameter are especially concerning because they have the potential to cause global disasters. Luckily, space agencies like NASA have already tracked over 90% of these large asteroids, and they are confident that none of them are currently on a collision course with Earth. However, smaller objects, while not capable of causing worldwide destruction, can still cause major regional damage. Events like the 2013 meteor that exploded over Chelyabinsk, Russia, and the 1908 Tunguska event in Siberia serve as reminders of the dangers small asteroids can bring. As we continue to discover and monitor NEOs, improving our planetary defense strategies is crucial. International cooperation and new technological developments will be essential to protect Earth. By understanding these space rocks and preparing for potential threats, we can ensure a safer future for all. Every few years, beneath the calm surface of the Pacific Ocean, a powerful force quietly stirs. It's a natural event so strong that it influences weather patterns across the entire globe. This force is known as El Niño. From the heavy rains that cause devastating floods in South America to the severe droughts that spark wildfires in Australia, El Niño is far from mere tropical curiosity. It's a global force that can throw the world's weather out of balance. El Niño, which translates to the boy in Spanish, happens when the water temperature in the Pacific Ocean rises by about 32.4 to 32.9 degrees Fahrenheit above average. This event was first noted in the 1500s, and since then, scientists have learned that its impact can be felt in every corner of the world. The effects of El Niño are far-reaching and dramatic. It can trigger flooding, droughts, rising levels of carbon dioxide, and shifts in global temperatures. This phenomenon typically begins in the central and eastern Pacific Ocean, but its reach extends far beyond. Countries near the ocean and coastal areas, especially developing nations, often feel the brunt of its effects. Additionally, marine life that is not adapted to sudden changes in temperature suffers greatly when the waters warm rapidly. El Niño's disruptive power leaves no part of the planet untouched, making it one of the most significant climate events in the world. El Niño isn't the only weather phenomenon that impacts the world's climate. El Niño is just one part of a larger climate system called the El Niño Southern Oscillation, ENSO. This system has three phases: El Niño, La Niña, and a neutral state. The neutral state is when neither of the two major phases is active, and there's no noticeable impact on the weather. La Niña, or the girl in Spanish, is the opposite of El Niño. While El Niño brings warmer temperatures, La Niña causes cooler temperatures in the ocean. During a La Niña event, water temperatures can drop by as much as 37 to 41 degrees Fahrenheit. This cooling effect leads to severe weather in many parts of the world, including the United States and Canada, where it can cause intense rainstorms, floods, and more powerful hurricane seasons. The most challenging part about El Niño and La Niña is that they are difficult to predict. They occur every 2 to 7 years, but not on a fixed schedule. These phases are not short-term events either. El Niño typically lasts 9 to 12 months, while La Niña can last 1 to 3 years. Both El Niño and La Niña don't just happen randomly. They are triggered by a complex process in the Pacific Ocean. Normally, trade winds blow from a high-pressure area to a low-pressure area, moving from east to west. These winds push warm water towards Asia and Australia, while cold water rises along the coast of South America. This upwelling of cold water is beneficial for marine life as it brings nutrient-rich waters that support fish populations. The warm waters in the west heat up the air above them, causing it to rise rapidly. This rising air helps create weather patterns that drive the trade winds, keeping them in balance. However, when this natural balance is disturbed, either by changes in the winds or the ocean currents, El Niño or La Niña can develop, leading to dramatic shifts in weather around the globe. During an El Niño event, the winds that normally blow across the Pacific Ocean weaken. This causes the warm surface water to be less disturbed by wind movements. As a result, upwelling, which normally brings cooler water from deeper parts of the ocean to the surface, also decreases. With less cold water rising, the ocean's surface temperature starts to rise evenly, even in areas that are typically cold. This shift in ocean temperatures has a far-reaching impact on global weather patterns, leading to significant changes in rainfall and overall weather conditions around the world. For instance, in tropical regions, the likelihood of flooding increases, while in Western countries, droughts tend to become more severe. A good example of this can be seen in Hawaii's protected area, Pu'u'o'o. Under normal conditions, the area receives about 2.7 inches of rain in January. However, during the El Niño event in 2010, only about 4 inches of rain fell, much lower than usual. Interestingly, El Niño is not a permanent condition. It can switch to a La Niña phase. During La Niña, the winds become stronger, which enhances upwelling and leads to the cooling of the ocean surface in certain areas. This can cause the western United States and northern South America to experience cooler temperatures, while some regions around the Indian Ocean may warm up. The areas most affected by these changes are those bordering the Pacific Ocean. The consequences of such dramatic weather shifts have been devastating in the past. In the 19th century, extreme weather events caused by El Niño and La Niña led to severe droughts and floods in places like India, China, and Brazil, resulting in the loss of 30 to 60 million lives. In the 20th century, there were 26 recorded cases of El Niño, a weather event that caused serious problems for the harvests of Western countries. It also hurt many animal populations, including sea lions. The countries most affected by El Niño were Peru and Ecuador in South America. These nations depend a lot on the export of fish and fertilizers, but El Niño messes up their economies. As a result, fish numbers drop because the rising of nutrients in the ocean decreases, leading to massive fish deaths. Also, the increased rainfall from El Niño washes away crops and fertilizers, damaging infrastructure in these areas. On the other hand, the dry conditions caused by El Niño affect countries in the eastern parts of the world, such as Indonesia and Australia. In these areas, water sources dry up and crops begin to die, which harms the health and well-being of both people and animals, as well as the fertility of the land. In Africa, countries like Kenya and Tanzania get lots of rain, while nations in southern and central Africa, such as Zambia and Mozambique, suffer from long dry periods. In the United States, especially in Texas, increased rain during El Niño leads to flooding, adding to the widespread damage caused by this unpredictable climate event. In California, for example, El Niño brings rain which helps the crops, especially limes and avocados, grow better. Interestingly, El Niño also affects Canada, where winters are becoming warmer. It even impacts Antarctica, making the western part of the continent warmer, which causes more snowfall. However, this warming creates problems too, as it reduces the risk of cold water, leading to the melting of shelf glaciers. On the other hand, La Niña, the opposite weather event, helps increase the size of these glaciers, which helps keep things balanced. The effect of El Niño on European countries is harder to measure, but it usually brings cold and dry winters, which can harm crops and land. For example, during the 18th century, El Niño hurt harvests in Europe, and some experts believe this might have played a role in the start of the French Revolution in 1789. In the 19th century, El Niño caused several serious famines across both Asia and Europe. These events show that both El Niño and La Niña are dangerous events for our planet. The last major El Niño event occurred in 2015 and 2016, almost 7 years ago. In 2016, the world saw the hottest year ever, and it was the most intense El Niño event in the past 50 years. This extreme weather pattern caused widespread hunger, affecting over 60 million people. During 2015, the waters of the equatorial Pacific Ocean were warmer than usual all year round. In November of that year, the central part of the ocean warmed by nearly 37.4 degrees Fahrenheit at its highest point, with an overall temperature rise of 35 degrees Fahrenheit. This warming is likely the highest since records began in 1860. El Niño has had a huge effect on almost every continent, either directly or indirectly, causing a chain of serious events. Take Australia, for example, where the impact was especially harsh. The eastern and northern parts of the country went through extreme droughts, which led to an unusually early start to the fire season. By the end of it, an incredible 125 fires had burned through large areas, including Tasmania's rainforests and swamps, places that had rarely, if ever, been burned before. On top of the fires, Australia's ocean life also took a hit. It was the worst coral bleaching ever recorded, a process that turns colorful corals white, making them weak and close to dying. On land, 2016 brought one of the driest springs and falls in Australian history, ruining crops and cutting harvests short. The intense heat even disrupted supplies of some of the country's key exports, which caused effects in global markets. Elsewhere in Asia, countries faced their weather troubles. In the Philippines and Indonesia, about 85% of the regions went through extreme droughts. Indonesia also dealt with widespread fires, which created thick, choking smoke that spread to Singapore, Malaysia, and Thailand, polluting their air. Each wavelength reveals a different feature of the Sun, offering a unique glimpse into its activities. The AIA's capabilities are groundbreaking. It can observe the Sun in 10 different wavelengths, each one tuned to detect solar material at specific temperatures. This allows scientists to see the Sun in a variety of colors, each color revealing something new about its surface and atmosphere. For example, cooler and darker sunspots appear in certain wavelengths, while blazing hot corona loops are visible in others. Over the past decade, the AIA has continuously observed the Sun, capturing more than 425 million high-resolution images. Each of these images adds to a constant flow of data, creating a detailed and ever-evolving picture of the Sun's dynamic behavior. This vast collection of images has been crucial in advancing our understanding of solar activity, from solar flares to massive eruptions. But why do we study the Sun so closely? The answer lies in the Sun's immense influence on our solar system. It is the central force that shapes everything from Earth's polar lights to weather patterns on distant planets. By studying the Sun, we gain insights into the fundamental processes that govern not just our planet, but the entire cosmic neighborhood we live in. In real time, the Solar Dynamics Observatory, SDO, has captured breathtaking images of the Sun, revealing the dynamic and ever-changing nature of our star. From sudden bursts of solar material being ejected to the twisting magnetic fields and the dramatic dance of solar flares, these events have been documented with extraordinary detail. The SDO didn't just give us a glimpse into the Sun's activity, it unlocked a deeper understanding of the complex forces that shape solar weather. Over the past decade, this continuous observation has offered an unprecedented look at the Sun's behaviors, shedding light on phenomena once only imagined. We've gained valuable insights into everything from solar flares and energy flows to the mysterious 11-year solar cycle. What was once pure speculation is now a subject of scientific study, thanks to the mission's detailed data. The SDO serves as a constant, vigilant observer, capturing every subtle change in the Sun with unparalleled accuracy. In its 10 years of operation, it has gathered over 425 million high-resolution images, building a continuous, evolving portrait of the Sun's surface and atmosphere. Picture a world where, every fraction of a second, a new aspect of the Sun's activity is revealed. The SDO achieves this by taking images every 75 seconds, allowing us to witness real-time changes and processes that were once invisible to us. The observatory's ability to study the Sun in different wavelengths of light has opened up exciting new ways of exploring our star. Each wavelength provides a unique perspective, revealing different layers of the Sun's atmosphere, from its turbulent surface to the farthest reaches of its corona. One of the most fascinating things that the Solar Dynamics Observatory, SDO, watches is the extreme ultraviolet light at a wavelength of 17.1 nanometers. This special wavelength allows us to see a part of the Sun that's usually hidden from view, the solar corona, which is the outermost layer of the Sun's atmosphere. The corona is a place full of intense solar activity where temperatures soar to millions of degrees. It's here that we find some of the Sun's most mysterious events, such as coronal mass ejections, CMEs, and solar flares. With the SDO's observations, the corona is no longer a dark, unclear area. Instead, it becomes a vibrant, dynamic region filled with activity. We can now see massive arcs of plasma called coronal loops, which are shaped and driven by the Sun's powerful magnetic field. These loops help us understand the complex behavior of the Sun, as we also witness huge explosions of solar material that send waves of energy streaming out into space. These observations are more than just beautiful images. They are crucial in helping scientists understand how the Sun's activities affect space weather, which in turn influences our planet. As the SDO continues its mission, every new image and piece of data adds to our understanding of the Sun's corona, showing us just how complex and active our star truly is. One of the most exciting challenges in solar science has been figuring out the 11-year solar cycle, a rhythm that has puzzled astronomers for years. This cycle involves regular changes in the Sun's activity, like the number of sunspots, solar flares, and CMEs. The SDO's decade-long observations cover almost an entire solar cycle, giving scientists an up-close view of how the Sun changes during both active and quiet periods. During times of solar maximum, the Sun is busy with sunspots and intense flares. But during solar minimum, it enters a quieter phase, with fewer sunspots and less overall activity. Over the course of its mission, the SDO has witnessed and carefully recorded countless solar events. It has captured massive eruptions of plasma, known as CMEs, in great detail, showing just how much energy is released when these explosions happen. Solar flares, bright bursts of radiation, have been studied at different wavelengths, providing scientists with key insights into what triggers these powerful explosions. But the excitement doesn't stop there. The SDO has also observed some rare and stunning moments when planets pass in front of the Sun. These events are not just visually thrilling, they also provide an excellent opportunity to study the Sun's atmosphere and its interactions with other planets. This adds another layer to our understanding of the Sun and its behavior, helping scientists to expand our knowledge of solar dynamics and how the Sun shapes the space around us. Space exploration is a journey filled with unexpected obstacles, each one unique in its way. NASA's Solar Dynamics Observatory, SDO, has encountered its fair share of these challenges, constantly pushing the limits of what can be achieved through creativity and perseverance. The mission has faced everything from Earth's shadow to lunar eclipses and malfunctions with crucial instruments. Despite these issues, SDO has always found a way to continue its groundbreaking work. One of the most frequent and challenging problems is the natural phenomenon of eclipses, caused by the Earth and Moon, which can temporarily block the observatory's view of the Sun. Eclipses are a regular part of SDO's orbit, but they still pose challenges. During Earth eclipses, which occur around the equinoxes, the Earth casts a shadow, plunging the observatory into brief moments of darkness. This creates a temporary loss of data as the Sun's rays are blocked. Similarly, lunar transits, though much rarer, can also obscure the observatory's view of the Sun, creating another tricky situation for solar observation. In 2016, SDO faced a more serious hurdle when its Atmospheric Imaging Assembly, AIA, one of the mission's key instruments, experienced technical problems. The AIA is responsible for capturing high-resolution images of the Sun's atmosphere, which are essential for understanding its complex behavior. Without this instrument functioning properly, the ability to monitor solar activity, particularly invisible solar events called coronal mass ejections, CMEs, was put at risk. CMEs are enormous bursts of solar wind and magnetic energy that explode from the Sun's outer atmosphere, the corona. These events often take place in areas where the Sun's magnetic fields are weaker, making them harder to detect. Unlike typical CMEs, which can be seen as dark spots on the Sun's surface, these invisible bursts are much more difficult to observe. It was a complex problem, but the SDO team refused to give up. They quickly found innovative solutions to visualize the solar data still being captured by the AIA. By comparing images of the Sun taken 12 hours apart, they were able to track slow changes in the lower corona. This method allowed them to identify subtle variations in the Sun's magnetic fields and plasma loops that had been previously overlooked. To make these tiny changes clearer, the team applied advanced image processing techniques, including wavelet packet equalization and multiscale Gaussian normalization. These methods helped bring out the faint signals of CMEs, making it possible to observe the hidden effects of these powerful solar events. Thanks to their creativity, teamwork, and determination, the SDO team turned what seemed like a major setback into a valuable breakthrough in solar research, revealing new ways to study the Sun's activity. As we take a closer look at the findings from the Solar Dynamics Observatory, SDO, we begin to understand just how deeply the Sun affects not only Earth, but the entire universe around us. Decades of data from the SDO have greatly improved our knowledge of space weather, what we call the energetic activity coming from the Sun, and its wide-reaching effects on our planet and beyond. Space weather refers to phenomena such as solar flares, coronal mass ejections, CMEs, and solar energetic particles. These events, which originate from the Sun's active surface and atmosphere, travel through space and can influence both planets and spacecraft. On Earth, the effects of space weather are fascinating, but they can also be serious. For example, when the solar wind and CMEs interact with Earth's protective magnetic field, they can create stunning displays known as the Northern and Southern Lights, auroras. However, this interaction can also cause major disruptions, such as problems with satellites, communication systems, and even power grids. Thanks to the findings from SDO, we've become much better at predicting space weather events. By studying the systems that cause solar eruptions and how they travel through space, scientists can now forecast when and how these events will impact Earth. This kind of prediction is crucial for protecting our technological systems both in space and on Earth. The significance of SDO's research stretches far beyond our planet. Understanding space weather is essential for the safety of astronauts in space, especially as we prepare for missions to the Moon, Mars, and other distant destinations. As we venture further into space, knowing how the Sun behaves becomes even more important. As we look toward the future of solar exploration, there's a world of hope and exciting possibilities ahead. The current era of studying the Sun is defined by groundbreaking missions like the Parker Solar Probe and the Solar Orbiter. Launched in 2018, the Parker Solar Probe has already ventured closer to the Sun than any spacecraft ever before. Soon, it will enter the Sun's outer atmosphere, known as the corona, and help uncover its many secrets. Meanwhile, the Solar Orbiter, a collaboration between ESA and NASA, launched in 2020, is designed to give us a never-before-seen view of the Sun's poles and outer atmosphere, regions that were once beyond our reach. Both of these missions are equipped with advanced technology, enabling them to study the Sun in ways we never thought possible. The Parker Solar Probe will travel through the solar corona, offering insights into the processes that shape the solar wind and the high-energy particles released by the Sun. The Solar Orbiter, with its unique orbit and sophisticated instruments, will allow us to study the Sun's magnetic field, atmosphere, and solar wind in unprecedented detail. Looking ahead, the future of solar observation is filled with incredible promise. There are endless opportunities for groundbreaking discoveries that could help us unlock the mysteries of the Sun's magnetic field, improving our understanding of solar flares and coronal mass ejections, powerful events that affect space weather. By studying the Sun's inner workings, we may also learn more about its 11-year solar cycle and how it influences conditions on Earth. The Parker Solar Probe, PSP, is a NASA space probe launched in 2018 with the groundbreaking mission of studying the outer corona of the Sun. The probe will get closer to the Sun than any spacecraft before it, coming within 6.9 million kilometers, 4.3 million miles, of the Sun's center. By 2025, it will reach speeds of up to 690,000 km/h, 430,000 Mach, which is about 0.064% of the speed of light, making it the fastest man-made object ever built. Designed and constructed by Johns Hopkins University Applied Physics Laboratory, the spacecraft was launched on August 12, 2018. It was named after physicist Eugene Newman Parker, a prominent scientist who predicted important solar phenomena back in 1958. His contributions earned him the honor of having the probe named after him, making it the first NASA spacecraft to be named after a living person. A special plaque on the spacecraft carries a memory card with the names of over 1.1 million people, alongside a photograph of Parker and a copy of his groundbreaking 1958 paper. The spacecraft made history on October 29, 2018, when it became the closest artificial object ever to approach the Sun, breaking the previous record set by the Helios 2 spacecraft in 1976. At its closest approach during perihelion on September 27, 2023, the PSP came as close as 7.26 million kilometers, 4.51 million miles, to the Sun. This distance will be surpassed in 2024 during another flyby of Venus. The Parker Solar Probe is the first spacecraft to venture into the Sun's lower corona. Its mission is to study the Sun's outer atmosphere and magnetic field, investigating how the Sun's energy heats its corona and drives the solar wind. The spacecraft will also explore how energetic particles are accelerated and transported through the Sun's corona and into space. To survive the intense heat and radiation near the Sun, the spacecraft is equipped with a special solar shield. When the probe gets closest to the Sun, it will face about 475 times the solar radiation intensity that Earth experiences. The shield, which is about 2.3 meters, 7.5 feet, in diameter, and 11.4 centimeters, 4.5 inches, thick, is made of carbon-based materials designed to withstand temperatures up to 1,170 degrees Celsius, 2,500 degrees Fahrenheit. This shield ensures that the spacecraft's instruments remain at a safe 29 degrees Celsius, 85 degrees Fahrenheit. The solar shield's design also helps minimize heat absorption with a reflective surface. The spacecraft relies on 4 light sensors to monitor any sunlight that may reach the shield's edges. If any sunlight is detected, the spacecraft quickly repositions itself using reaction wheels to stay within the protective shadow of the shield. This autonomous system ensures that the probe stays safe from the Sun's extreme heat, even though communication with Earth takes about 8 minutes each way. Powering the probe is a system of solar panels. When the spacecraft is farther from the Sun, it uses a primary array of panels. As it gets closer to the Sun, a smaller secondary array kicks in, providing power through a cooling system to maintain the spacecraft's temperature. The primary goals of the Parker Solar Probe mission are to understand how energy flows through the Sun's corona, how the solar wind is accelerated, and what processes shape the solar wind's speed and direction. It aims to explore the structure and behavior of the Sun's magnetic fields, figure out how these fields connect with the solar atmosphere and how they influence the solar wind. It also seeks to uncover the mechanisms that accelerate particles in the Sun's corona and track their movement through the solar system. Through this data, scientists hope to better understand the Sun's influence on the space environment around Earth and beyond. The Parker Solar Probe is equipped with 4 main scientific instruments that provide crucial insights into the Sun's behavior and its surrounding environment. The Electromagnetic Fields Investigation, FIELDS. This instrument suite measures the electric and magnetic fields in the Sun's atmosphere. It helps scientists understand how these fields behave, including how waves, shocks, and magnetic reconnection, a process where magnetic field lines suddenly rearrange themselves, occur. FIELDS uses 5 antennas to capture electric fields around the spacecraft. 4 of these antennas extend beyond the spacecraft's heat shield into the sun's extreme sunlight, where temperatures soar to 2,500 degrees Fahrenheit, 1,270 degrees Celsius. These long antennas, made from a heat-resistant niobium alloy, are designed to survive such intense heat. The instruments capture electric fields across a wide range of frequencies, studying both the fast and slow solar wind, the continuous stream of particles from the sun. Additionally, Fields has 3 magnetometers: a search coil magnetometer to monitor rapid changes in the magnetic field closer to the sun, and 2 flux gate magnetometers for studying slower changes farther from the sun. The principal investigator for Fields is Stuart Bale from the University of California, Berkeley. The Integrated Science Investigation of the Sun, ISIS. This set of instruments measures particles like electrons, protons, and ions, helping scientists track their journey from the sun to interplanetary space. ISIS includes 2 devices, EPI low and EPI high. EPI low measures the spectra of low-energy particles, identifying elements like carbon, oxygen, and iron, as well as 2 types of helium isotopes. Understanding these particles' acceleration mechanisms could reveal much about their origin. EPI high is designed to measure higher energy particles and uses ultra-thin silicon detectors to determine particle direction and reduce noise. The detailed readings from EPI high will allow the probe to detect up to 100,000 particles per second when it's closest to the sun. The principal investigator is David McComas from Princeton University. The Wide Field Imager for Solar Probe, WISPIR. This instrument uses 2 cameras to capture images of the sun's corona and the inner solar system. The cameras are equipped with radiation-resistant sensors and lenses made from durable BK7 glass, which can withstand impacts from dust particles in space. The principal investigator is Russell Howard from the Naval Research Laboratory. The solar wind electrons, alphas, and protons, SWEEP. This investigation measures the properties of particles like electrons, protons, and helium ions. It uses 2 key instruments: the Solar Probe Analyzer, SPAN, and the Solar Probe Cup, SPC. SPC, a metal device placed just outside the heat shield, collects charged particles by using highly transparent grids to sort them based on their energy. This allows scientists to track the particles' velocity, temperature, and density. The instrument can take up to 146 measurements per second, providing an accurate snapshot of the sun's plasma. SPAN, which includes 2 components, detects the particles that SPC might miss. The principal investigator is Justin Casper from the University of Michigan and the Smithsonian Astrophysical Observatory. In addition to these core instruments, there is a theoretical investigation called Heliospheric Origins with Solar Probe Plus, HelioSPP, which provides input on the spacecraft's scientific performance. It helps maximize the mission's overall scientific findings, with Marco Velli from the University of California, Los Angeles, and the Jet Propulsion Laboratory leading the team. On 25 September 2022, the Parker Solar Probe made its first comet discovery, named PSP's Joosta 1. The comet was spotted in images from 29 May 2022, taken during the spacecraft's 12th pass near the Sun. Since then, 19 other comets have been discovered in its images, adding exciting discoveries to the mission's portfolio. In 2024, the Parker Solar Probe also detected a rare event known as the Kelvin-Helmholtz Instability, KOHI, during a solar eruption, becoming the first spacecraft to observe this long-theorized phenomenon. The Solar Orbiter, SOLO, is a spacecraft designed to study the Sun, developed by the European Space Agency, ESA, with help from NASA. Its main job is to take detailed measurements of the inner part of the solar system, called the heliosphere, and to track the early stages of solar wind. The spacecraft will also study the Sun's polar regions, something that's very hard to do from Earth. These observations are essential for understanding how the Sun creates and controls its vast magnetic bubble known as the heliosphere. The Solar Orbiter spacecraft is designed to face the Sun directly. It is a 3-axis stabilized platform, which means it keeps its position and orientation stable as it moves. To protect it from the intense heat near the Sun, the spacecraft is equipped with a special heat shield. This shield ensures that the spacecraft can safely get close to the Sun without overheating. The spacecraft has a stable setup that supports both remote sensing, observing the Sun from afar, and in situ, measuring directly, experiments. It has 21 scientific instruments, carefully arranged so that each one can perform its work while staying protected from the Sun's harsh environment. Some of the Solar Orbiter's technology comes from earlier space missions, like the solar panels from the Bepi-Colombo mission, which is going to Mercury. These panels are designed to rotate and adjust to avoid getting too hot when the spacecraft is close to the Sun. The spacecraft also has a battery pack to provide extra power when it's not in direct sunlight, such as when it's in the shadow of a planet during a flyby. To stay in contact with Earth, the Solar Orbiter uses a Telemetry, Tracking, and Command Subsystem, TT&C. This system helps send data back to Earth and allows controllers to send commands to the spacecraft. The spacecraft communicates through a system of antennas, including low-gain antennas during the early stages of its journey, and more powerful steerable medium and high-gain antennas later on. The high-gain antenna is crucial for sending large amounts of data back to Earth. It can point in many directions to establish a connection with the ground station and transmit scientific data. This antenna was adapted from the Bepi-Colombo mission and can fold back to stay safe from the spacecraft's heat shield if needed. Most of the data is stored on the spacecraft and sent back to Earth when the spacecraft is in the right position. The mission's communication with Earth takes place through a ground station in Malargüe, Argentina. This station uses a large 35-meter, 115-foot antenna and operates for about 4 to 8 hours each day. There are also backup stations in New Norcia, Australia, and Cerbero, Spain, that can step in if necessary. During regular operations, the spacecraft sends its science data back to Earth in 8-hour blocks, and additional passes are scheduled to make sure all the data is returned. The mission makes the most of ESA's existing infrastructure for deep space missions. This includes the ground stations in the ESA Space Tracking Network, STRAC, the Mission Operations Center, MOC, in Darmstadt, Germany, and the Science Operations Center, SOC, in Spain. The SOC handles planning, mission coordination, and managing science data, while the MOC takes care of spacecraft operations. When the mission enters its active science phase, the SOC takes over responsibility for the spacecraft's science activities. During its initial cruise phase, which continued until November 2021, the Solar Orbiter spacecraft performed 2 gravity assist maneuvers around Venus and 1 around Earth. These gravity assists helped adjust the spacecraft's path, steering it closer to the inner regions of the solar system. During this phase, Solar Orbiter also collected important data to fine-tune its instruments, preparing them for their main mission. The first close pass by the Sun occurred on March 26, 2022, at about 1/3 of the distance between Earth and the Sun. The spacecraft's orbit was specifically designed to be in resonance with Venus. This means that, with every few orbits, the Solar Orbiter passes near Venus, using the planet's gravity to adjust and tilt its path. While a Solar Orbiter initially follows a path along the same plane as the planets, each time it passes Venus, its orbit shifts slightly. For instance, after its 2025 encounter with Venus, Solar Orbiter will make its first solar pass at a 17-degree tilt, which will increase to 33 degrees during a planned mission extension, allowing it to observe more of the Sun's polar regions. Every 6 months, the spacecraft makes a close approach to the Sun, allowing scientists to study the same regions of the solar atmosphere repeatedly. These close passes will give Solar Orbiter the ability to closely observe the magnetic activity in the Sun's atmosphere, including the buildup that can lead to powerful solar flares and eruptions. The Solar Orbiter team is working with NASA's Parker Solar Probe, which is also studying the Sun, focusing on its extended corona. They are also collaborating with ground-based observatories like the Daniel K. Inouye Solar Telescope. Together, these efforts aim to provide high-resolution, close-up studies of the Sun and the surrounding space environment, enhancing our understanding of the Sun's behavior and its effects on the solar system. The spacecraft carries a range of specialized instruments to study the Sun and solar wind in detail, like the Solar Wind Plasma Analyzer, United Kingdom, SWA, a suite of sensors that measures the solar wind's ion and electron properties such as density, speed, and temperature. It also analyzes the solar wind's composition, focusing on key elements like carbon, oxygen, iron, and magnesium. The Energetic Particle Detector, SPAIN, EPD, measures the timing, composition, and distribution of energetic particles, shedding light on their sources and the processes that accelerate them. The Magnetometer, United Kingdom, MAG. It provides precise measurements of the heliospheric magnetic field, helping scientists understand how the Sun's magnetic field connects to space and evolves during the solar cycle. The Radio and Plasma Waves, France, RPW, measures both electric and magnetic fields to study the electromagnetic waves in the solar wind, offering insights into the dynamics of solar wind and space weather. The Polarimetric and Helioseismic Imager, Germany, PHI, provides high-resolution images of the Sun's surface and interior, helping scientists study the solar magnetic field and the convection processes within the Sun. The Extreme Ultraviolet Imager, Belgium, EUI, captures the solar atmosphere, focusing on the outer layers and helping to connect surface activity with the outer corona. The Spectral Imaging of the Coronal Environment, France, SPICE, uses extreme ultraviolet imaging to analyze the Sun's corona, linking solar wind streams with their sources on the Sun's surface. The Spectrometer Telescope for Imaging X-rays, Switzerland, ASTIX, measures X-ray emissions from the Sun, helping to study solar flares and microflares by providing data on accelerated particles and high-temperature plasmas. Metis, Coronagraph Italy, captures the Sun's corona in both visible and ultraviolet light, providing critical information on the structure and dynamics of the corona, which is key to understanding solar activity and the solar wind. The Solar Orbiter Heliospheric Imager, United States, SOLO-HI, observes solar wind disturbances and helps identify coronal mass ejections, CMEs, which can impact space weather. In 2022, the Solar Orbiter and the Parker Solar Probe teamed up to explore why the Sun's outer atmosphere is much hotter than its surface. By observing from different distances, Solar Orbiter from 140 million kilometers and Parker Solar Probe from just 9 million kilometers, scientists were able to compare data from both missions. In March 2024, both probes will make their closest approaches to the Sun, with the Parker Solar Probe coming within 7.3 million kilometers and the Solar Orbiter at 45 million kilometers. This close collaboration between the two missions will provide a unique opportunity to compare their observations of the Sun's behavior and solar wind. Recent discoveries made by the James Webb Space Telescope have uncovered a hidden treasure: rocky, carbon-rich exoplanets orbiting tiny stars. These faraway worlds may hold the key to understanding the origin of life, offering the perfect conditions for creating the basic building blocks of life. Thanks to its advanced infrared capabilities, the James Webb Space Telescope has detected carbon dust similar to diamonds, dating back to the earliest stars in the universe. This carbon dust is essential in the creation of stars and planets, and it turns out that it may also play a crucial role in forming life itself. What makes these exoplanets particularly exciting is their rich carbon content, a fundamental element for life as we know it. Carbon forms the backbone of organic chemistry, the process that drives life on Earth. These planets may provide just the right conditions to develop complex organic molecules, which are necessary for life to emerge. Around these miniature stars, where conditions are stable and long-lasting, rocky planets with carbon-rich environments could serve as ideal laboratories to study life's origins. Could this mean we need to rethink where life might exist beyond Earth? To better understand where life could thrive, it's important to know how planets and life-supporting ingredients form. Life can't exist without a planet, after all. The building blocks of planets and the life they could support are found in vast spinning disks of gas and dust that surround young stars. These protoplanetary disks are where planets are born, and they're also where the complex chemistry that leads to life begins. Recent observations using powerful tools like the Atacama Large Millimeter Array have uncovered a wide variety of organic molecules within these disks, such as methane and acetylene. These molecules form through complex chemical reactions in the cold, dense regions of the disks. When gas and dust collide and the materials are exposed to ultraviolet radiation from the central star and cosmic rays, they create these crucial organic compounds. These organic molecules are vital because they represent the early steps in the evolution of life. Simple molecules like these are the precursors to more complex compounds such as amino acids and nucleotides, which eventually build proteins and DNA. The discovery of these molecules in protoplanetary disks suggests that the building blocks for life might be widespread across the universe, naturally forming as planets are born. To better understand these processes, scientists have used the James Webb Space Telescope to conduct laboratory experiments. These experiments have expanded our knowledge of the chemical composition of protoplanetary disks. The telescope's high-resolution infrared observations have provided detailed insights into the chemical processes happening in the early stages of planetary system formation. Scientists have detected key molecules like water, carbon dioxide, and complex organic compounds, showing the diversity of the chemical environment in these disks. One key discovery made by the James Webb Space Telescope is the mapping of these molecules across the disk. This map shows how the chemical makeup of the disk changes as you move farther from the central star, revealing areas rich in ice and organic compounds, ingredients crucial for planet formation. These findings suggest that, as young planets form, they may incorporate these organic molecules in ice, which could later contribute to creating habitable environments. Understanding the chemical composition of protoplanetary disks helps us learn more about how planets form and evolve. The presence of organic molecules and other complex compounds suggests that the basic ingredients for life are built into the very process of planet formation. As these molecules are incorporated into developing planets, they might be preserved in comets and asteroids, which could then deliver them to the surface of planets through impacts. The dynamic chemical processes occurring in these disks also show how forming planets interact with their environment. For example, the mixing and movement of materials within the disk can lead to different planetary compositions and atmospheres. This chemical diversity is crucial for creating varied planetary environments, some of which may also be suitable for life to develop. One of the most exciting discoveries made by the James Webb Space Telescope was the finding of diamond-like carbon dust from some of the universe's earliest stars. This unusual find gives us new insights into how the cosmos began to take shape. The telescope's strong infrared sensors can pick up even the faintest signals from faraway objects in space. By studying the light emitted from ancient stars, scientists found traces of carbon dust that resemble diamonds. This carbon dust isn't just something to look at. It plays an important role in the formation of stars and planets. Early in the life of a star, carbon dust acts like a cooler, helping to lower the temperature of the gas inside a cloud of dust and gas. As the cloud cools, it becomes dense enough to collapse under its gravity, eventually forming a star. Without this cooling effect, the process would be too slow for stars to form. As stars grow older and reach the end of their life cycles, they release carbon-rich materials into space, which mix with the gas and dust around them. This process seeds the space between stars with the ingredients needed for the birth of new stars and planets. Carbon dust also plays an important role in the creation of protoplanetary disks, clouds of gas and dust that surround young stars. These disks are where planets are born. In these disks, the carbon dust particles can stick together and grow, eventually forming the building blocks of rocky planets. The discovery of diamond-like carbon dust suggests that even the first planetary systems, which formed shortly after the Big Bang, might have had the necessary materials to create planets. This is a big deal for our understanding of the early universe. It shows that carbon was already present in large amounts, even in the universe's early stages. This finding raises the possibility that the ingredients for carbon-based molecules, and perhaps even life, may have existed much earlier than we once thought. The presence of this carbon dust also helps scientists piece together a timeline of the universe's development. It shows that the first stars, known as Population 3 stars, played a crucial role in enriching the cosmos with heavy elements like carbon. As these stars lived, burned through their fuel, and eventually exploded, they scattered their carbon-rich materials across space. This helped to make the universe more chemically complex, setting the stage for the formation of planets and life. A carbon-rich environment is important for the development of complex life forms. While other elements are important too, carbon is special because of its unique ability to form stable, complex molecules. Carbon can bond with up to 4 other atoms at once, allowing it to create a wide variety of organic compounds that are essential for life. This flexibility allows carbon to form long chains and rings, which are the building blocks of proteins and other molecules that are necessary for organisms to function and thrive. An even more fascinating and groundbreaking discovery came when a team of over 40 scientists from across the globe used the James Webb Space Telescope, JWST, to explore the protoplanetary disks around small stars. These disks, which are regions where planets form, provided a detailed view of a star called ISO-Chi 147, located in the Chameleon Y star-forming region. The study revealed the most diverse collection of hydrocarbons ever found in a planet-forming disk, including the first-ever detection of ethane outside our solar system. The discovery of ethane is revolutionary because this simple hydrocarbon plays a crucial role in the chemistry of life. Ethane can serve as a building block for more complex organic compounds, suggesting that the basic ingredients for life could be more common in the universe than we previously thought. What's even more exciting is that the protoplanetary disk surrounding this tiny star seems to be particularly good at forming small, Earth-like planets rather than large gas giants like Jupiter. This is significant because low-mass stars are much more common in the Milky Way galaxy, meaning there could be far more small, rocky planets out there than we had originally imagined. The chemical composition of the protoplanetary disk around ISO-Chi 147 is rich in carbon-based molecules like ethane and benzene, but it has very few oxygen-rich molecules like water and carbon dioxide. This is a stark contrast to the disks around stars like our Sun, where oxygen-rich molecules are more abundant. The abundance of these hydrocarbons in such large amounts suggests that material within the disk is being transported across it in a radial direction, affecting the composition of the planets that form from it. These differences in chemical makeup mean that rocky planets around small stars might have atmospheres that are very different from Earth's. For instance, many of these planets could have atmospheres filled with hydrocarbons rather than oxygen, which could lead to the development of carbon-rich planets unlike our own. This discovery is vital because it deepens our understanding of the possibility of life elsewhere in the universe. Carbon is the fundamental element in organic chemistry, forming the backbone of DNA, proteins, and other essential molecules. Finding hydrocarbons like ethane in protoplanetary disks suggests that the building blocks of life might be widespread across the cosmos, naturally forming during planetary creation. The findings also highlight the complex and dynamic processes at play in protoplanetary disks. One potential explanation for the imbalance of carbon and oxygen in these disks is an enrichment process where solid particles lose their carbon content, releasing it as gas. These carbon-deprived particles eventually form rocky, carbon-poor planets, but their atmospheres remain rich in carbon-based gases. Understanding the difference between carbon-rich and oxygen-rich disks is key to determining the potential for life on planets around small stars. Planets in carbon-rich environments with hydrocarbons like ethane could support life forms based on biochemical processes completely different from those on Earth. On the other hand, planets formed from oxygen-rich disks, which contain water and carbon dioxide, might have conditions more similar to those that led to life's emergence on Earth. This chemical diversity opens up the possibility that planets forming in these two types of disks could have radically different atmospheres and surface conditions. This could lead to entirely new forms of life or prebiotic chemistry that we have yet to imagine. The discovery of rocky, carbon-rich exoplanets around small stars not only expands our understanding of planetary systems, but also boosts the hope that life beyond Earth could be detected one day. Small stars, where these carbon-rich exoplanets are likely to orbit, are abundant in our galaxy. These stars are often more stable than larger ones, providing a steady environment for billions of years and giving life plenty of time to evolve. This stability increases the chances that life could emerge and develop. But while carbon is essential, it's just one part of the puzzle. What other elements and conditions are needed for life to exist? In the search for life beyond our solar system, scientists focus on a concept known as the habitable zone, also called the Goldilocks zone. This is the region around a star where the temperature is just right for liquid water to exist on the surface of a planet. Liquid water is essential for life because it serves as a solvent, helping to create the complex chemical reactions needed for biological processes. The location of a planet's habitable zone depends on the type and size of its star. For smaller, cooler stars, the habitable zone is closer to the star, while for larger, hotter stars, it's farther out. Finding planets in these zones is one of the key challenges for astronomers who are looking for worlds where life might exist. One of the tools that's helping in this search is the Habitable Zone Planet Finder, HPF. Located on the Hobby-Eberly telescope in Texas, the HPF is designed to detect exoplanets, planets outside our solar system, around low-mass stars by measuring tiny changes in the star's light caused by the gravitational pull of orbiting planets. This instrument is especially good at finding planets in the habitable zones of dimmer, cooler stars, which are more common in our galaxy. The HPF has allowed astronomers to make significant strides in discovering planets that could potentially support life, increasing the chances of finding planets that are similar in size to Earth but would otherwise be missed by other instruments. In this context, an unexpected and fascinating discovery has raised new questions about how planetary systems form, revealing that the universe is more diverse than we once thought. The discovery of LHS 3154b, an exoplanet that is much larger than expected for its small star, suggests that there are processes involved in planet formation that we don't fully understand yet. Traditionally, models like core accretion, the idea that planets grow by gradually accumulating material, and disk instability, where planets form from the collapse of gas and dust around a star, suggest that the mass of the star should limit the size of planets that can form around it. But LHS 3154b doesn't follow this pattern. It could have formed farther from its star and then moved inward, or it may have been captured from another star system. These possibilities challenge current theories about how planets form and evolve. What's particularly surprising about LHS 3154b is that despite its size, it's located in the habitable zone of its star, meaning it has the potential to support liquid water. This raises the possibility that habitable zones could exist under a wider range of conditions than we once thought. However, having such a large planet in the habitable zone of a small star could affect the habitability of other nearby planets. The gravitational pull of the large planet might influence the climate and geology of smaller, potentially habitable planets nearby, either stabilizing their conditions or making them more unstable. This means that LHS 3154b could play a significant role in determining the chances for life on other planets in the system. The surprising size of LHS 3154b also brings up new ideas about how planets evolve. It could represent a stage in planetary evolution that we don't yet fully understand. For instance, some gas giants may lose their atmospheres due to intense radiation from their star or gravitational interactions, causing them to shrink in size and mass. This process is known as planetary evaporation or shrinkage. In the case of LHS 3154b, its large mass and unusual orbit suggests that it may have once been a larger gas giant that lost part of its gas envelope or was affected by its star's dynamic environment. These new findings challenge the idea that only Earth-like planets orbiting Sun-like stars can be habitable. They suggest that life might be able to exist in a variety of surprising environments. One of the key players in this exciting journey of discovery is the Transiting Exoplanet Survey Satellite, TSS, which was launched in 2018. TESS is designed to scan the brightest stars near Earth, looking for planets that pass in front of them, a phenomenon known as a transit. Its main mission is to identify thousands of new exoplanets, ranging from Earth-sized to massive gas giants, and provide valuable targets for further research using other telescopes. So far, TESS has already uncovered many planets, some of which are located in habitable zones, regions where conditions might be right for life to exist. These planets are now prime candidates for more detailed study. In 2029, the European Space Agency will launch the Ariel mission, which will focus on studying the atmospheres of 1,000 exoplanets. By analyzing the chemical makeup and heat signatures of these distant planets, Ariel will help scientists learn more about how planetary systems form and evolve. It will also provide valuable insights into the potential habitability of these worlds. Looking even further ahead, proposed missions like Louvois and Habex have the potential to revolutionize exoplanet research. These missions aim to directly capture images of exoplanets, especially those that resemble Earth, and search for signs of life, such as oxygen and methane, in their atmospheres. By studying the light that bounces off these planets, scientists hope to detect biomarkers, indicators that life might exist or have once existed on these distant worlds. With so many exciting missions on the horizon, the future of exoplanet research looks incredibly promising. As we learn more about these faraway planets, the big question still lingers. Are we truly alone in the vast universe, or is there life out there, just waiting to be discovered? By now, most of us are familiar with the idea that life first began in the ocean. However, there are still many questions that stir up passionate debates among scientists. For example, how did life make the incredible leap from water to land? Why might a massive meteorite impact have played a crucial role? Did a collision with another planet help jumpstart the development of life on Earth? What did our planet look like during the first few million years of its existence, and what kinds of challenges did it face in those early days? While some of these questions still leave experts puzzled, many of them have already been answered. Let's take a closer look at what we know so far. The idea that life started in water and later moved to land seems like a very believable theory. After all, more than 70% of Earth's surface is covered by oceans, which are full of life. Many of the creatures living in these vast waters are still not well understood, and scientists are constantly finding new species. Over time, some of these early water-dwelling organisms adapted to life on land, eventually changing into the complex beings we are today. This brings to mind Darwin's well-known theory of evolution, where a brave fish supposedly decided to vacation on dry land, setting the stage for the development of land-dwelling creatures. Although this story is often simplified, scientists still use Darwin's theory as a base for understanding evolution. It raises an interesting question. What exactly is needed for life to form, beyond just having an ocean? To explore this, we must go back billions of years to the very birth of the solar system. Around 13.6 billion years ago, scientists believe the universe was born in a huge event known as the Big Bang. This event not only shaped the universe, but also created the first building blocks of matter. Hydrogen, the simplest element, was formed and began to gather together under intense pressure and heat. This process eventually led to helium, a new element. Groups of hydrogen that went through this change are called protostars. These young, fiery masses were the early forms of stars, but their existence was short. Their story marks the beginning of a cosmic chain of events that would eventually lead to the creation of planets, oceans, and ultimately, life itself. The main advantage of these processes is the creation of new chemical elements, which became the building blocks for life. First, this led to the birth of ordinary stars. Every star has its life cycle, where it functions like a massive factory. Within it, things are constantly burning, producing smoke and flowing with streams of resources. All of this leads to the creation of new substances. These processes also have an impact on the environment around them. Our sun, just like any other star, follows this pattern, but on a cosmic scale. The life of a star is quite ordinary, though. It either expands into a supernova, transforms into a red giant, or becomes a white dwarf, followed by a slow decline and death. In some cases, a star might collapse into a black hole. We know for certain that our sun will one day become a red giant, expanding to engulf nearby planets, including Earth. However, that won't happen for another 5.5 billion years, so we have plenty of time left, enough to finish watching all our favorite TV shows. Scientists believe the sun was formed from the explosion of a supernova that occurred near the area where our solar system was born. This supernova caused gas clouds to collapse under their gravity, forming the sun. Over time, the sun absorbed so much matter that it didn't just create itself, it created the entire solar system. Anything that wasn't part of the sun began to spin around it, eventually flattening into a disk shape. A vast amount of matter was involved, and some of it became planets, while the rest either drifted off to become comets or dwarf planets. The Earth, which would eventually become the cradle of humanity, began forming in this cosmic chaos. Early Earth was like a giant molten stew of lava, rocks, and hot gases. The temperature on the surface was over 1200 degrees Celsius, and there was no breathable air, only carbon dioxide, nitrogen, and steam. The planet was constantly being bombarded by comets and meteorites, some pulled in by Earth's gravity, and others by the sun's. This is where the water that would later cover Earth came from. But at this stage, life didn't even exist. The most significant event in Earth's history was yet to come. A planet-sized object, about the size of Mars, collided with Earth. This impact, while catastrophic, turned out to be incredibly important. It was from this collision that the Earth we know today took shape. The impact gave Earth its current size and form, setting the stage for the creation of life in the distant future. Even more importantly, the pieces from a huge crash eventually formed our satellite, the Moon. At first, the Moon was much closer to Earth, about 13,600 miles away. This closeness had a big effect on the planet, and its importance would become even clearer as Earth cooled down over time. As Earth's temperature began to drop, its outer layer started to form, creating a thick layer of air. This was all the material Earth had gathered through gravity as it was forming. After the cooling process, only the very center of the planet, made of melted iron, stayed hot and liquid. It's the activity within this center that creates Earth's magnetic field, which helps keep the planet stable, allowing it to spin around its axis and circle the Sun. As Earth's temperature continued to fall, the planet had its first rainfall around 3.8 billion years ago. This rain wasn't like the showers we see today. Earth was hit by meteors from the leftovers of the solar system's formation. Though these meteors were filled with bits of rock, they also contained something very important: water. The speed of Earth's rotation was so fast at that time that a day only lasted about 6 hours, but thanks to this rain, Earth's first ocean began to form. For 20 million years, Earth was hit by meteor showers, and even though each meteorite contained only a small amount of water, the huge number was enough to create oceans. Scientists started to wonder, where did Earth's water come from? There are two main theories. One suggests meteorites brought the water to Earth, while the other proposes that water already existed on Earth. Over time and through discoveries, scientists realized both theories were partly right and partly wrong. Studies of the Moon's soil showed that the Sun, in its early stages, burned off everything that could evaporate from the planets, including water and gases. This means scientists still can't say for sure whether more of Earth's water came from meteorites or from the planet itself, and they might never be able to answer that question for sure. But the key point is that the crash of Earth with a planet-sized object called Theia started the cooling process of the planet, leading to the formation of Earth's atmosphere. This atmosphere would go on to protect Earth from the Sun, creating the shield needed to support life. Even though Earth had cooled, volcanic activity was still happening. The heat from the volcanoes caused water to turn into vapor, forming clouds that eventually turned into rain. For millions of years, rain fell to the Earth's surface, collecting into lakes, seas, and oceans. This vast ocean was wild. The Moon, which was much closer at the time, played a huge role in the strong tides, causing massive ocean storms. Some waves could reach heights of 1,000 feet, and the winds were nearly as fast as the speed of sound. Picture the ocean in a wild storm. This is the world where life is about to begin. Modern ideas generally agree that the Earth's oceans back then were the perfect place for life to begin. But there's still a big question. How did organic matter, the basic building blocks of life, form under these tough conditions? Let's break it down further. To understand how life began on Earth, we need to look back at the conditions of the ancient planet, focusing on the elements that made up the early atmosphere, like nitrogen, hydrogen, and carbon dioxide. These were inorganic elements, meaning they weren't alive. However, in the 1920s and 1930s, two scientists, Oparin from the Soviet Union and Haldane from the UK, developed theories that suggested life began from these very elements. They proposed that the Earth's oceans were constantly receiving organic substances from the atmosphere, which was constantly being struck by lightning due to ongoing storms. This electrical energy was key in turning inorganic chemicals into organic compounds, which eventually made their way into the oceans. Once there, these organic compounds began to gather together, creating a broth of life that would slowly develop into living organisms. These early particles behaved in a way similar to cells, growing, dividing, and absorbing other chemicals. But life didn't just form from this organic soup. It needed something more, the genetic instructions that would organize and direct these processes. In our cells, that guiding force is DNA, which acts as the blueprint for life, while RNA carries out the instructions. This theory is sometimes compared to the story of Frankenstein, where inanimate material is brought to life by lightning. For millions of years, life on Earth was nothing more than single-celled organisms. They weren't in a rush to evolve, partly because the conditions of the ancient Earth wouldn't have allowed more complex forms to emerge. These early organisms were prokaryotes, simple cells without protective membranes or nuclei, much like bacteria today. Then, around 3.5 to 2.5 billion years ago, a major change happened. These simple organisms figured out how to use sunlight, water, and carbon dioxide to create glucose, a simple sugar that served as their food. This process, called photosynthesis, also released oxygen as a byproduct, which began to build up in the atmosphere. This was a huge turning point because it set the stage for oxygen-breathing organisms to take over the planet. However, life faced challenges along the way. Two massive ice ages, the Pongola glaciation and the Huronian Ice Age, almost wiped out life. The Huronian Ice Age, in particular, was triggered by an oxygen catastrophe. Photosynthesizing organisms had produced so much oxygen that it poisoned many of the life forms that couldn't survive with it. This led to the rise of aerobic organisms, those that needed oxygen to live. As Earth's conditions began to change, life evolved further. Prokaryotes eventually gave rise to eukaryotes, more complex cells with structures like a nucleus. These eukaryotes were better equipped to compete, survive, and even destroy their rivals. Over time, they spread to land, driven by volcanic activity, and created the first forms of life we would recognize as trees, like stromatolites. These early life forms were red algae, which developed the ability to reproduce sexually, a crucial step for future evolution. Around 540 million years ago, the Cambrian explosion occurred, rapidly increasing the variety of life on Earth. This was followed by the appearance of the first animals, such as plankton and small marine creatures. Some 70 to 80 million years later, many species we recognize today began to take form. The first creatures to leave the water were arthropods, which began searching for more nutritious food on land. They didn't return to the water. Among the fascinating creatures to transition from water to land was the Tiktaalik, a fish with limbs like paws that allowed it to crawl out of the water. For the next 360 million years, plants began reproducing by seeds and spreading across land. Insects took to the air, and amphibians evolved into four-legged creatures known as tetrapods, adapting to life on land by laying eggs that could survive outside water and eating a variety of foods. These animals eventually gave rise to reptiles, birds, and primates. However, a major extinction event, the Permian extinction, wiped out 90% of marine life but left land species relatively unharmed. The Earth's ecology slowly recovered over the next 90 million years. Then, the age of dinosaurs began, only to end in a mass extinction caused by a meteorite impact. Yet birds and many other species survived, and life continued to evolve.